at the end of the last video, we saw something known as free body diagram, right? I guess you remember that. FBD, which is free body diagrams. Free body diagrams, as the name implies, involves freeing the body from the system and showing just the associated forces along with associated forces with the body. For example, we know that if we have a trolley, okay, we have a trolley, a man is holding it, okay, and it's on the floor. If we have a question like just draw a free body diagram for the trolley over here, what will we do? Just take the diagram as it is. It has its own weight, right? And over here we have a reaction for the roller support, okay. Roller support has a reaction. Even we could take this out, we can show just the vertical reaction, and it has its own weight, which is mg, okay, vertical support, and man is pushing, right? So that force, which is P, for example. So now we have roller reaction, trolley's own weight mg, and one man is pushing. So we took out all the forces associated with this trolley. So this is known as free body diagrams. This is very useful for solving any kind of problems in trusses and frames. And not only this, even if you go for any other topic in engineering mechanics, it's very useful. Fluid mechanics, strength of materials. If you want to be an expert in all these subjects, you'll have to be an expert in free body diagrams. But it's very simple. It makes the complicated of complicated questions as simple as possible. So that's the beauty of this free body diagram, and if you could draw this, it's going to be very damn easy. Okay, I'll just show you one more example so that you could understand it very well. So assuming I'm having a wall, string is attached to it, I'm having a flow, Miss mass M is there, okay, mass M is connected to the ground. Okay, draw the free body diagram of mass M. Okay, what will we do? Mass M, string force, right? String force is there, mg is there acting downwards, and normal force given by the earth, mg. And if there is a friction, okay, we show it like this. If it's moving in this direction, friction will be in the opposite direction. If it's moving in this direction, friction will be in the opposite direction. This is friction force. If we could show all the forces associated in a particular body like this, I could term it, or many researchers term it, this to be the free body diagram. Okay, so if you could know this, it's going to be very easy to solve any kind of problems. I'm sure about it. So next topic is going to be equilibrium. Okay, equilibrium, as is said, as the name implies, it's equal. Okay, if there is any kind of body, okay, for example, I am having some kind of same mass, let me say, we have a mass over here, some kind of cotton box, or some kind of big cotton box is placed on the floor. Nobody is doing nothing, right? So it stays still. Now, if I am going to apply a force P, okay, I am going to push, I am going to move it, okay, I am trying to move it, and I am moving it as of now. If there is someone who is resisting the force minus P, what will be the condition of mass M? It will stay still. Okay, equilibrium is a condition in which body stays still because whatever the forces associated with that is getting resolved using the counter forces. So I'll get you an example. Assuming I'm having a pad, okay, and this is the mass M. What am I going to do is I'm going to push this using a force P. Is it moving? Yeah, it is moving, right? It's very easy. If you have eyes, you should believe that. Okay, it's moving. Now what am I going to do is I'm going to resist this mobile phone or the mass M using my finger. I'm going to apply a force P. It's moving, touch, down, stop. Okay, equilibrium. It stays still because force P of this finger in my right hand is getting resisted by the thumb, force minus P of the thumb in the left hand. So it's getting resisted, it stands still. So this position is known as equilibrium position. Without this equilibrium position, the body or the concerned system will be in a movement. Okay, so that's what we have shown it over here too. Now for example, we could say from this diagram, sum of horizontal forces x direction. So normally we take like this, right, in India, xy, and this is going to be z. So x direction, sum of forces in x direction is going to be 0 because it's in equilibrium, it's standing still. Okay, not only for this, even if you take any kind of structures, I'll show you. So assuming I'm going to have a structure, okay, like this, pin joint or roller joint. So this is a structure. I could say each and every point is in equilibrium. For example, okay, I'm going to write it as A, B, C, D, E, F. Point A is in equilibrium, point B is in equilibrium, point C is in equilibrium, point D, every point is in equilibrium. So that we could apply summation of horizontal forces equal to 0. Now what about vertical force? So if I am going to apply a force 2P in the vertical direction, obviously it's going to get resisted from the earth is going to resist the 2P force as minus 2P. Okay, so it's going to be very simple concept. Same thing, I'll take the mass M. Okay, I'm going to apply a vertical force. If I'm not going to resist the force using my this left hand, what will happen? It will go down, right? It's going to go down like this. But if I'm going to resist it, I'm applying a force here like this, I'm trying my hard as I can, but left hand is not allowing me actually. No, you should not go, it's saying it's that way. Now I'm going to apply a force, it's getting rejected. Okay, so now this part is in equilibrium. Otherwise, if I'm going to apply a force, it's going to go down. Okay. So now summation of vertical forces in the y direction is going to be obviously 0. Next we are going to get introduced to a new concept known as moment. Moment is something m equal to force into perpendicular distance. Okay, so this is the formula. I could say force into perpendicular distance. Okay, how could I understand this? It's very easy actually for you to understand. I'll just take an example now. Okay, assuming I'm having, okay, it's like this and it's going to come out, right? So I'm holding it like this. So which is force into perpendicular distance like this. Okay, so which is force into perpendicular distance is the moment. Now both multiplies to get a moment. Now what I'm going to do is I'm going to try the same using the finger over here. Will I be able to resist? No, because force into distance is very low. Distance is low. As a result, moment is low. I can't resist it. In this, the same kind of concept could be understood in the concept known as torque. What is torque actually? That is also force into radius by the formula definition. But for you to understand as of now, assuming we have a nut and a spanner. Okay, what will you do? If the spanner is of small size, we just turn it somewhat in a difficult way. But if the spanner is of larger length, we just move it easily. So moment is force into perpendicular distance. For example, if you have a structure over here and if we have a point P over here, okay, P into this distance, for example, this is L and this is L, moment about point A, okay, moment about point A is going to be P into force into perpendicular distance 2L. Okay, from this facts I could say for a system to be in equilibrium, summation of moment about A is going to be 0, moment about B 0, all the points is going to be 0. Okay, now if you could understand 1, 2, 3, just taking out summation of moment equal to 0. So if you could understand this, you have done a great deal, and you have gone through the introduction, and after seeing some simple stuff after this section, you are going to solve trusses and frames problems by yourself. It's going to be damn easy, I'm damn sure. Follow us, you are going to be amazed, I'm sure. Wait and watch.